Hi everyone. From this session onwards, we will be discussing about solid state structures. As part of our syllabus, we have to discuss about structure of compounds of AX type, example, zinc blende and woodside structures, then structure of compounds having AX2 type formula, examples are fluorides and antifluorides, structure of compounds of the formula ABX3, for example, perovskites and ilmenite structures. Then we also have to discuss about spinel and inverse spinel structures. So in the following sessions, we will see each of these structures in detail. Before that, let us have some basic idea about structure of solids, especially three-dimensional closed packing. You might have heard about hexagonal closed packing, right? Where the crystal planes are arranged as AB, AB sequencing. In cubic closed pack structures, the sequencing is in the order ABC, ABC, which is equivalent to FCC, face-centered cubic closed pack structures. What are voids? Voids are vacant spaces in closed pack structures. Voids can be of different types like octahedral voids and tetrahedral voids. Octahedral voids are surrounded by 6 touching spheres, whereas tetrahedral voids are surrounded by 4 touching spheres. Number of octahedral voids within a unit cell will be equal to the number of atoms or number of motifs present within that unit cell, whereas number of tetrahedral voids will be double the number of atoms or motifs present in that unit cell. Here n is the number of spheres present per unit cell. In order to get a clear idea about all these concepts, just as a review, let us see a video.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all 3 directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the 3 types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all 3 dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, ionic compounds, adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell.
This animation has been taken from YouTube channel and the reference is given here. Now let us watch another video from this reference that would give us a clear picture about the octahedral and tetrahedral voids found in these crystal systems. Let us watch it.
The face-centered cubic lattice contains 8 atoms at the 8 corners of a cube and 6 additional atoms in the faces of the cube. Although the face-centered cubic lattice is often drawn to emphasize the cubic nature of the structure, it is also a close-packed structure. The face-centered cubic results from the stacking of close-packed layers in an ABC fashion, so that the fourth layer lies over the first layer, the fifth layer lies over the second layer, and so on. Here we use color to represent the 3 close-packed layers in the face-centered cubic lattice. Two types of spaces, or holes, exist between the layers of close-packed structures. The first type of hole is called an octahedral hole and is formed between 3 atoms in one close-packed layer and 3 atoms in a second close-packed layer immediately above or below the first. The space at the center of a face-centered cubic is actually an octahedral hole and is formed by 3 atoms in the green close-packed layer and 3 atoms in the blue close-packed layer. Despite the name, it takes 6 atoms, not 8, to define an octahedron. The term octahedron is derived from the fact that such a polyhedron has 8 sides. The center octahedral hole is the only one that lies entirely inside the cell shown here. Other octahedral holes lie partially inside this cell. The center octahedral hole shares each of its 12 edges with 12 other octahedral holes. 8 of these are shown here. Each of these lies 1/4 inside the cell. Overall, an array of n atoms in a close-packed structure actually gives rise to n octahedral holes. The second type of hole that exists between the layers of close-packed structures is called a tetrahedral hole. Tetrahedral holes are formed between 3 atoms in one close-packed layer and a single atom in a second close-packed layer immediately above or below the first. As before, we will switch to transparent polyhedra to represent the tetrahedral holes in our face-centered cubic lattice. The cell shown here contains 8 tetrahedral holes at the 8 corners of the cube, and these lie entirely inside the cell. An array of n atoms in a close-packed structure gives 2n tetrahedral holes. Several different ionic lattices adopt structures in which one set of ions form a face-centered cubic array and the other set of ions occupies the octahedral or tetrahedral holes. Halite is the mineral name for sodium chloride. In the halite structure, the relatively large chloride ions, represented by the green spheres, form a face-centered cubic array. The sodium ions, represented by the white spheres, occupy the octahedral holes. Each sodium ion lies at the center of an octahedron of chloride ions. Since an array of n close-packed atoms give n octahedral holes, and since there is one sodium ion for every one chloride ion, all of the octahedral holes are occupied. In contrast, the tetrahedral holes are vacant.
Hope these videos might have helped you to refresh your prior knowledge on crystal systems and crystal packing. I'll be right back on the next day with more videos on structure of solids. Thank you.